Hello, everyone, and welcome back to the deep dive. Today, we are doing something very specific and, very high yield for your exams.
Yeah.
We're looking at Unit 6, haloalkanes and halorines. And if you've looked at the syllabus or the insert book, you'll know there's a section at the very end.
The one everyone skips.
Exactly. We are talking about polyhalogen compounds.
It is good to be here. And you are so right. Most students skip this because they're focused entirely on, say, SN1 and SN2 mechanisms or the named reactions.
Right.
They think polyhalogen compounds. It's just theory. I will memorize it the night before.
That is such a classic mistake. I was looking at the past year papers, and the reasoning questions from this section can be really tricky. If you don't understand the concept, you can't just memorize the line.
Exactly. You need to understand the behavior of the molecule. So our mission today is simple. We're going to crack the logic behind these compounds, things like chloroform, iodophreons, DDT.
Okay.
We want to understand what happens when you stack multiple halogens onto a single carbon skeleton.
And to get our brains working, I want to start with a challenge. A chemistry riddle, basically.
I am ready. Let's hear it.
Okay. Imagine we're in the school chemistry lab. You have two bottles on the table. Both have clear liquids inside.
Okay.
Bottle A is chloroform, that's CHCl. And bottle B is carbon tetrachloride, CCl.
Okay, so structurally, the only difference is bottle A has 3 chlorines on the carbon, and bottle B has 4, just 1 extra chlorine.
Correct. Now, here's the puzzle. You take a test tube with aqueous potassium hydroxide, KOH, and you add it to both bottles. In bottle A, with the chloroform, you see a reaction. It gets cloudy, some chemistry is happening. But in bottle B, with carbon tetrachloride, absolutely nothing happens. It just sits there.
2 separate layers, like oil and water.
Uh-huh.
A very standard observation, yes.
But wait, here's my doubt. In organic chemistry, we usually say that adding a halogen makes the carbon more reactive. No, because the halogen pulls electrons away.
That's the inductive effect, yeah.
Yes. So logic says, if I have 4 chlorines in bottle B, it should be even more reactive than bottle A. But it's actually inert. It doesn't react at all. Why? Why does adding more chlorine make it stop reacting?
That is the million-dollar question. And frankly, if you can answer that, you understand this entire topic. The answer is that reactivity is not just about how many halogens you have.
It's something else.
It's about the geometry and the availability of a weak point to attack.
So we're going to solve this riddle by the end of the deep dive.
Definitely. But first, let's make sure we're on the same page with the basics. For a student sitting in class 12, how do we define these compounds properly?
Well, looking at the notes, at the simplest level, polyhalogen compounds are just organic compounds that contain 2 or more halogen atoms.
On the same carbon skeleton, yes.
Right.
Correct. Imagine a simple methane molecule, CH, a central carbon with 4 hydrogens. If you replace 1 hydrogen with a chlorine, that's a monohalogen compound. That is what you study for most of the chapter. But here, we are imagining 2, 3, or even all 4 hydrogens being replaced by halogens.
So it's like a crowded house.
That is a great way to describe it. It's crowded. And when you crowd that carbon atom with big halogens like chlorine or bromine, 2 major things happen at the particle level. First is the inductive effect.
Okay, let's break that down. Halogens are electronegative.
Very. Think of every halogen as a powerful little vacuum cleaner. It's sucking electron density away from the central carbon.
So if you have 3 or 4 vacuums,
Running at once, yes. That carbon becomes extremely electron deficient.
it's being starved of electrons.
Correct. And the second factor is steric crowding. Halogens are, well, they're fat atoms compared to hydrogen. They take up a lot of space. So when you put 4 of them around 1 carbon, they physically block the way.
So the result is that the properties change completely. Boiling points go up, polarity changes, and as we saw in the riddle, chemical reactivity changes.
Yes. And here's a clarity line I want students to note down. This is the kind of sentence that gets you marks. Polyhalogen compounds contain multiple halogen atoms. Their reactivity and properties are influenced by the cumulative effects of multiple halogens.
Cumulative effects. I like that phrase. It means they add up.
They do, but, and this is the big warning, do not fall into the trap of thinking more halogens equals more reactivity.
That's exactly what I thought at the start.
It is the most common misunderstanding. You assume reactivity is just additive. But sometimes adding more halogens makes the compound locked in.
Inert.
And inert, yes.
Let's use an analogy to make this stick, because inertness can be a hard concept to visualize.
Okay, let's try the power plant analogy. Imagine the carbon atom is a power plant.
Okay, I'm picturing it.
If you have one generator running, that's 1 halogen. It creates some power, some pull, The system is active.
Right.
But in carbon tetrachloride, CECl, you have 4 generators running at maximum capacity.
So the system is overloaded.
In a way, the electron withdrawal is so intense and the pull is coming from all directions that the system becomes saturated. It's balanced in its intensity. It becomes stable because it is maxed out.
It resists change because it can't handle any more input.
Exactly. But I think for the riddle we started with, why CKIL doesn't react with the base, the fortress analogy works even better.
I love a good mental movie. Let's do the fortress.
Close your eyes for a second.
Yeah.
Picture the carbon atom as a king sitting in a fortress.
Okay, the carbon is the king.
Now look at chloroform, CH-CoLo. You have 3 guards, those are the chlorines, standing around the king. But there is one open spot. There's a hydrogen atom there.
And hydrogen is small. It's not much of a guard.
Exactly. It's a weak point.
Yeah.
Now, the enemy is the base, the Yoki ion
Yeah.
it wants to attack. In chloroform, because those 3 big guards are pulling all the resources, all the electrons away.
The king is weak.
The king is weak, and that single hydrogen is barely hanging on.
So the enemy can just easily snatch the hydrogen away.
Precisely. The base attacks the hydrogen, pulls it off, and boom, the reaction is started. That's why you saw the reaction in bottle A.
Because there was a weak point, a handle to grab.
Yes. Now, picture carbon tetrachloride, CCl, in bottle B. You have 4 big guards, 4 chlorines, completely surrounding the king.
It's a sealed
A
fortress.
sealed fortress. There is no hydrogen.
No weak point.
No hydrogen. And the guards are so big and standing so close together that the enemy, the base, it can't even get close to the carbon. It physically cannot reach the center.
So the base just bounces off.
It just bounces off. There is no angle of attack.
Mm-hmm.
That is why CCl is inert towards hydrolysis. It's structurally protected.
That makes total sense. So for the exam, if they ask why is CCl inert, the answer is the absence of a CH bond and steric shielding.
Spot on. And for chloroform, the reactivity is due to the acidic nature of that single hydrogen.
Wait, acidic? I thought acids were things like HCl or HESOA. How is chloroform acidic?
It's a term we use in organic chemistry. Acidic here just means a hydrogen that is easy to remove as an He ion.
Ah.
Because the 3 chlorines are pulling electrons so hard, the carbon, in turn, pulls electrons from the hydrogen. That CH bond becomes weak, and the hydrogen becomes acidic.
Got it. So that is why the base grabs it so easily.
And this leads us to a very important named reaction mechanism. The haloform reaction.
Oh, right. The iodoform test comes from this logic, doesn't it?
Exactly. Chloroform, bromoform, iodoform, they all have that CHXE structure with the acidic hydrogen. That is why they react.
And CCl does not have it?
CCl does not have it, so it does not give that reaction.
That connects the dots perfectly. Okay, I have another doubt that always confuses me. It's about polarity.
Go ahead. This is the nonpolar paradox, isn't it?
Yes. Okay, listen to my logic. We know the carbon-chlorine bond is polar. Chlorine is electronegative. It creates a dipole.
Correct. Each CCl bond is polar.
So if CCl has 4 of these super polar bonds, it should be the most polar molecule ever. It should mix with water easily, but the book says CCl is nonpolar. How is that possible?
This is a guaranteed question in board exams or entrance tests. The confusion comes because you're looking at the bond polarity, not the molecular polarity.
What's the difference?
You have to look at the geometry, the shape of the molecule. CCl is a regular tetrahedron.
A tetrahedron.
Yes. Imagine the carbon in the center, and the 4 chlorines are at the corners of a pyramid, all pulling outwards.
Okay, so it's like a 4-way tug of war.
Exactly. A perfect 4-way tug of war where every team is equally strong and pulling at perfect symmetrical angles. What happens to the rope in the middle?
It doesn't move. The forces cancel out.
That is it. The individual bond dipoles are strong, but because of the symmetrical structure, the vector sum of all those dipoles is 0. We call this dipole cancellation.
So the net result is 0 polarity for the molecule.
0. That is why CCl is nonpolar. And because it dissolves in other nonpolar things like oils, but it hates polar water.
Okay, I am going to ask you for the exam-safe clarity line for this. If a student needs to write this in one sentence, what do they say?
Right. You should write this down. Do not confuse bond polarity with molecular polarity.
Okay.
CKIL possesses polar CCl bonds, but the molecule itself is nonpolar because the symmetrical tetrahedral geometry causes the bond dipoles to cancel each other out.
Vector sum is 0. That is the key phrase the examiner is looking for.
Yes. If you don't mention symmetry or vectors, you will lose marks.
Okay, let's shift gears. We've talked about the lab, but why did we even bother making these compounds? I mean, apart from giving students headaches, Do they have a real use?
Oh, they were massive. In fact, they changed the way we live. We have to talk about the industrial revolution of these chemicals.
You are talking about things like freons, aren't you?
Yes. Back in the early 20th century, we had a problem. We needed fluids for refrigerators and air conditioners.
Right.
The stuff they used for, like ammonia, was toxic and flammable. If your fridge leaked, you could die.
Not ideal.
So chemists looked for something that was non-flammable and extremely stable. And they found polyhalogen compounds, specifically chlorofluorocarbons, or CFCs.
We call them freons.
We call them freons, yes.
Yeah.
Like Freon 12, dichlorodeifluoromethane, a carbon with 2 chlorines and 2 fluorines. It's incredibly stable. You can compress it, expand it, heat it. It doesn't break down. It was the perfect solution.
But there's always a but.
The but is that they were too stable. And this brings us to the environmental crisis, the ozone hole.
Right. We all know CFCs are bad for the ozone, but as a chemistry student, I need to know how. What is the mechanism?
It's a radical mechanism. Because CFCs are so stable, they don't break down in the lower atmosphere, the troposphere. They drift up intact for years and years until they reach the stratosphere.
Where the ozone layer is.
Yes. And up there, the UV radiation from the sun is very, very strong. It hits the CFC molecule, and it's strong enough to break the CCl bond.
Through homolytic fission, right?
Through homolytic fission, correct.
Yeah.
So the bond breaks evenly, creating free radicals.
And it releases a chlorine-free radical, a Cl dot.
Correct. And this radical is a serial killer for ozone.
Why? I mean, does it just react once and it's done?
No, that is the scary part. It initiates a chain reaction. The chlorine radical reacts with ozone, OO, to form oxygen, ORO, and a CLO radical. Then that CLO radical reacts again to release the chlorine radical back.
So the chlorine radical comes out alive at the end to kill another ozone molecule.
Exactly. It's a catalyst for destruction. One single chlorine radical can destroy thousands of ozone molecules. That is why even a small amount of CFCs is so dangerous.
So the clarity line here is about stability becoming a trap.
Yes, environmental persistence. The lack of reactive CH bonds and high stability allows CFCs to reach the stratosphere, where UV light generates chlorine radicals that deplete the ozone layer.
That is a solid answer. Now there is one more villain in this story, DDT.
DDT. A classic example. This is another polyhalogen compound, and it was the first major modern insecticide. It was effective because, again, it was chemically stable. It stayed on the fields and killed bugs for months.
But again, stability was the problem.
Yes. The problem here is a different concept, though. It's called bioaccumulation.
This is important. Explain this for us.
DDT is fat-soluble, not water-soluble. Remember our rule. Like dissolves, like DDT is nonpolar, so it doesn't wash away in rain. It dissolves in the fatty tissues of animals.
So if a small fish eats a bug with DDT, the DDT gets stuck in the fish's fat.
Correct. It doesn't leave the body. Then a big bird eats that fish. Now the bird has all the DDT from all the fish it ate. The concentration increases as you go up the food chain. That is bioaccumulation.
And that caused the bird populations to crash, right? Because of the eggshells.
Yes, it thinned their eggshells. It is a classic lesson. Chemistry isn't just about making a molecule. It's about understanding its entire life cycle.
This has been a really comprehensive look. We have covered a lot of ground. I want to make sure the students listening have a solid summary to take away. Let's recap the main points.
Sure. Let's break it down into 4 takeaways.
Takeaway number 1, the core concept.
Polyhalogen compounds have multiple halogens on one carbon. This causes intense electron withdrawal, the inductive effect, and also steric crowding.
Takeaway number 2, the reactivity logic.
Remember the fortress. Chloroform reacts because it has a weak point, that acidic hydrogen. CCLO is inert because it has no hydrogen and is sterically shielded.
So it's about the angle of attack.
Exactly.
Takeaway number 3, the paradox.
CCl has polar bonds, but is a nonpolar molecule. Why? Because of vector cancellation due to its symmetrical geometry. Don't forget the vectors.
And takeaway number 4, the environment.
Stability is a double-edged sword. Whether it is CFCs reaching the stratosphere or DDT accumulating in fat tissues, the very thing that makes them useful also makes them persistent pollutants.
That is a perfect summary. You know, it is funny. We started with a riddle about 2 bottles, and we ended up talking about the ozone layer in eagle eggs.
That is the beauty of chemistry, isn't it?
Oh.
It connects the microscopic structure, the shape of one molecule, to the macroscopic world.
So for everyone listening, when you are revising Unit 6, don't just memorize the uses of freon. Think about the why. Think about the fortress and the power plant.
Absolutely. If you understand the logic, the marks will follow.
And one final thought to leave you with. If stability causes these environmental problems, how do we design new chemicals that are stable enough to use, but just unstable enough to break down before they destroy the planet? That is the future of chemistry.
A very important question.
Thanks for tuning in to the deep dive. Good luck with your preparation, and we will catch you in the next one to crack another topic.
All the best, everyone.